Okay, so what I was saying is today, this class is going to be delivered by Angeliki. She's going to be your TA for this course, and she's going to talk all about OpenQuake. Okay. Okay, I'll dare to start the video too. So it's all about OpenQuake. Hopefully, everybody has installed OpenQuake on their computers. Yes, no, hopefully. And if not, Angeliki can give you some pointers, but the instructions are all online. Worst case scenario, if you have like real problems, we can reconnect Thursday around 2:30. If not, you just let us know, okay? That's important. Now, it's important that you also run these exercises that Angeliki is going to prepare for you on your computer. Otherwise, you're going to have trouble when you try to do anything else. I mean, it's important to get meshed up with OpenQuake and actually run things. Otherwise, it doesn't make sense, right? There's also going to be some Q&A. Am I right?
Yes.
Excellent.
We will visualize the results of our analysis there.
Super, excellent. So guys, hopefully Qgis is also installed. That should be even more straightforward. Download it, run it. All the instructions are online. You can even do it as we speak if you've not done it already. But it should be fairly obvious, okay? So shall we start, I guess, Angeliki? Oh,
Yes.
one more thing. Apologies, one more thing. We're gonna have to finish by 11 local time. So let's say 2 hours and 10 minutes from now. So Angeliki is gonna have one break in the middle. She'll know. And also, please remember that whoever will take the course for credit, please send me a declaration of a little town. Remember that one? About 1,000 or more inhabitants in the Cycladics, okay? Cycladic Islands. Just send it to me so you register that. By the way, those of you, and there are many of you who have already sent it to me, I will reply within, let's say, the end of the day. By the end of the day, I'll reply to you and say, okay, this is the one. The only reason being that if somebody else has declared this, the same one, in advance, or if somebody has declared something really large, somebody told me they want the entire island of so and so, we can reduce that a little bit. So the assumptions we make for the project actually work, okay? So you don't get weird results. Otherwise, you should be fine. And with that, I give you over to Angeliki, and I'll be around, but won't be talking too much. Okay, Angeliki?
Thank you. Good morning from me, guys. Let me share my screen. Okay. I think you can see it now. Do you see my screen? Okay, thank you very much. Together, we will talk about OpenQuake. We see how it is structured and some of its basic parameters. OpenQuake, as Mr. Vamvatsikos told you, will be useful for us in order to run our analysis and for you to run your term project.
Sorry, Angeliki, can you
Yes?
maximize your screen? Can you go to full page or something?
That's perfect. I'm sorry for that. We won't repeat. Okay, we talked about OpenQuake. Well, OpenQuake is an open source software that helps us calculate seismic hazard and risk. Seismic hazard aims to predict the future shaking on a region that we want to study. When we will know the shaking, the next thing we can do, if we want also, is to find the consequences of the buildings of the structures we have. Here we can see a map of Greece that shows us the seismic zones. When one of us wants to design a building or a structure in general, we have to decide where the structure will be located, and Eurocode gives us the acceleration at the bedrock. But why do we care about that? Well, seismic hazard assessment does the same for us, but a little better, I think. Those are the outputs we expect from our analysis. When we perform a seismic hazard assessment, the output may be a seismic hazard map. On a map like this, at every point, we can know the value, the ground motion parameter that we want. In this case, this is a map that shows peak ground acceleration at every point with a specific probability of exceedance in a given time span. For example, we have here peak ground acceleration with 10% probability of exceedance in 50 years. The next thing we can have, if we don't want a map, is some hazard spectra. A hazard spectra gives us the spectral acceleration values for a range of periods given a constant probability of exceedance. With the red color, we can see the uniform hazard spectrum we produced from OpenQuake, and the other two spectra is from Eurocode. We know that the black one is for zone 1 and the blue one is for zone 2. You know what spectra is, you have used them, but you can see that those results are not exactly like Eurocodes. That's why we prefer them in order to have not better results, but more precise, I would say. Okay, when we want to design a structure, we need a finite element model. Now that we want to assess the seismic hazard on a region, don't we want something like that? Of course we do. We need a model that gives us all the details for the seismic sources we will have on the area that we will study. How can we do that? In order to simulate the seismicity is the seismic search model that we will use. We have two options. First of all, the easiest one is to use seismicity and faults, but this is not easy if we think that not all faults are shown. We don't know all the details for all the faults that exist. In this case, if we do know, we can use this option and to say that an earthquake is produced by a well-defined fault and a well-defined rupture. I'm stopping here. Am I too fast? Do you follow me? Do you have any questions?
We're following, it's fine.
Okay.
Yes, we follow.
Thank you. As we said, if we don't have a specific fault, we have another option. In this case, we use distributed seismicity. In distributed seismicity, we say that earthquakes can happen everywhere, anywhere, here, there, with the same probability of exceedance. We don't know where, but we know that every point has the same probability of exceedance. Okay. So if we choose this kind of seismicity, we can perform the analysis. We have three options. I'm moving that. I don't know if it's different. Well, the first option in this category is to use a point source. A point source considers that the rupture, here we don't have faults, we have ruptures where earthquakes are produced. So we think that the rupture is generated under a single point over here that we can see. And it is simulated by a planar surface that the rupture is. Of course, we can use also a grid source that is a collection of point sources. We won't have only one point source, we can have more. There is a final option where we consider exactly that at every point, an earthquake, a rupture may happen. From a computation point of view, those two options are the same, area and grid sources, because we have to provide to OpenQuake a list of point sources where the rupture will be. I'm sorry. Okay. Now let's move on seismicity and faults. We said that here we have a specific fault. How can we simulate it? Well, first of all, we can use a simple fault. A simple fault is generated by the projection of the fault trace over depth. The fault trace is the intersection between the fault and the surface of the Earth. It is simple. It's just a line or a polyline, I would say, that we project over depth. This is what we will use today on one of the examples we will see in OpenQuake. Of course, we can use a more complex fault. In this case, we have a surface that changes width and inclination always. This is not constant. These values are not constant. Finally, we have a third option where the fault is simulated by a set of planar surfaces, and this is the whole fault. Do you have any questions? Something that you don't understand that you would like to ask?
I'm not sure I understood the difference between a simple fault and a complex fault.
Okay. The simple fault is just a line with specific characteristics that we can see that better here. Let me move on. I think there is a slide where, okay, there is not. Okay, if we have a simple fault, then we have only the fault trace on the surface of the Earth. This could be a line, let's say a simple line. We use that line.
So the fault is a surface, and how is the intersection of the surface with the surface of the Earth is the fault trace, and if this is a simple line, this is a simple fault.
Michalis, it's actually easier. You start with the fault trace, okay? And then it's like you said, you project along the deep direction. So let's say the deep direction is, I don't know, 30 degrees downwards. Okay. So you just take this line, project 30 degrees downwards, you translate along the depth, and that's your fault zone, let's say. That's your fault area. The complex fault is the opposite. It actually has a very complex shape that may change if you look at it. You might see that it starts, let's say, very shallow, and then it starts going very deep. To give you an idea, subduction faults are like this. If you know about them, Mexico, you remember the earthquakes in Mexico City, right? The recent ones, the older ones, 85. Actually, if you remember, those faults, theoretically, are way out in the shore of Mexico. But in reality, that is the part where they go deep, and then they go fairly shallow and actually reach fairly inland into Mexico. So this change in deep, you cannot do it with a simple fault. You have to use a complex fault. Simple fault is essentially a single dip that goes down, so it's fairly easy. Okay.
Thank you very much. Are there any other questions? We will see them again and we will use them on our examples. I swear they will be more clear in the future. Okay. Here we will see how we can simulate a point source. Point source is used for distributed seismicity. Remember that. So we have a rapture. Our rapture is a rectangular surface. For that, we have to specify the inclination, exactly what Mr. Van Vadzikos told us. So I have the inclination of the rapture of my plane, and I have also the orientation of the fault. The orientation is the angle between a horizontal plane and my rapture. We can see some examples over here, a 0-degree angle, a 90-degree angle, and many more. Finally, we have to specify the depth of the hypocenter. We said that this is a source where it is generated under a single point. That point is the hypocenter. Okay. So I have an area distributed source in this case, and we have said that earthquakes can occur anywhere with equal probability. We saw what the point source is on the previous slide, and we also said that we have to give as an input a list of point sources where our area will be. Okay. Let's move on simple faults. We saw a simple fault also earlier. This is the fault trace, and this is the projection of the fault trace. So this is our fault. In order to simulate our rupture, where the earthquake will happen, we have to discretize it, and when this area is shaded, this is our rupture. Because we don't know where exactly the rupture will happen, we think that the rupture floats all over our fault and it can happen anywhere. Any questions?
I have a question regarding the area source. So
yes.
you mentioned that the earthquake could happen anywhere in the area. So for the area source, we assume that all the earthquake that could occur would be point source, or there is the potential that there would be like simple fault. I mean, like earthquake with fault also.
So the question is, if we have an area source,
Yeah.
if an earthquake on a simple fault won't happen? If we can have both cases, a simple and a grid source? Is this the question?
I mean, I don't really understand the area source, because you say like any earthquake could happen in that region. So when you define it, you define only like a point source, or you could also define like a finite fault, like from those different earthquakes that could happen there.
Actually, can I help a little bit? Sorry, can I help a little bit here, guys?
Yeah, thank you.
Now, remember our discussion about discretization? This is all that's happening here, okay? It's about discretization. Now remember, there is a reason why we have two alternative fault models. And by the way, both are used at the same time, okay?
Okay.
Now, the characteristic faults, the finite faults, is when you actually know the faults. These are faults that produced earthquakes in the past.
Yeah.
And because they've produced earthquakes in the past, because you can trace them by their aftershocks, foreshocks, etc., you have some rough idea.
Yeah.
If they have a surface projection, even so better, okay? Sometimes they don't, but you know those things. So those faults, it's like it's there, you know, it's rough dimensions, you can more or less put it in there. And if you have even better information about its 3D structure, you make it a complex fault with all the little dips and angles, etc., etc. Now, the problem is that there are many, many places in the world that you do not have well-defined faults.
Yes.
Plus, even if you had them, you know that there are faults lurking in there that you've never seen, activated. A classic example for it would be like the Athens earthquake that happened in 1999, which was a fault that nobody knew, and it didn't even break ground. So like nobody really exactly knows where that is, except from the aftershocks. And of course, the question is it the only one that we do not know of? Same goes for Italy. For example, lots of earthquakes in Italy do not have identified surface projection or even identified faults. They just happen on a new one. Like, whoa, surprise every time. So to cover for that, what you do is you pretty much say, okay, guys, it's a possibility that earthquakes can happen anywhere in this area. So here is a coverage of that. And if you do not know better, that's why you assume equal probability. If you do not know, you have no information, it's not likely that a specific spot will be a hotspot. You say like, okay, whatever, equal probability. That's like simplest uniform uncertainty thing. If you do have information, you can break up into smaller area sources and assign higher probability to some areas than others, okay? That's why you'll see area sources being broken up in pieces. So you cover a huge area with little broken pieces. Actually, the seismic hazards to the source model for Italy is more or less small area faults. Small area sources. Okay? So it's a combination of those things. In the end, again, remember, it's all about discretization.
Oh, see, I see.
Yeah, it's all about discretization. So essentially, let's say you break up your country, the area of interest, to areas that you assume they have similar seismicity, hence uniform, etc., probability of or rate of events. And then each of those areas, to put that uniform rate into, let's say, reality, into Monte Carlo, you do Monte Carlo, you break up in those little grid points. You see those points? That's the whole thing. And of course, each of those little grid points, like Angeliki said, can break up into a rupture on its own. Of course, now remember, usually area sources, you do not allow to go to large magnitudes. Okay, you don't go like like the really big earthquakes. Because the whole idea is, if this was a fault capable of producing such kind of event, we would have seen some movement. Okay? We would have kind of identified it. So usually those are reserved for like up to 6s, 6 point somethings. Usually that's the range that you play with those area sources. So don't expect something that just ruptures the whole thing, okay? So sorry for that. I'm trying to clarify.
Yeah, it's very clear. Thank you very much.
Sure. It's a good question, by the way. Thank you.
Okay, let's move on. I think we have stopped over here. Well, now that we have specified our seismic search model, we know what are our sources, but we don't know what are the magnitudes of the earthquake that will happen. Each seismic source is associated with a model that gives us the distribution of earthquake magnitudes. So for each source I will have, even if this is a simple fault or an area source, at every point I know that I have a distribution for magnitudes. So for a given magnitude, I know the probability of occurrence. If I want to use a nice recurrence law, is Gutenberg-Richter's. So I have a source, and for that source, I have a distribution that shows me for each magnitude, which is the probability of occurrence. Okay, so far? This is not something difficult. Of course, even if this source is a simple fault, or if it is a point source, its rupture is associated with the earthquake magnitude. The higher the rupture of the area of the rupture, the higher the magnitude of the earthquake. You understand that? If this is a bigger rupture of the fault, this will be more devastating. Okay. Let's see something else. We said that we have our sources. Are we 100% sure that we have only one type of sources? No, we are not. If we want to consider all the cases for our seismic sources, we have to use a logic tree. This tree is something like that. It helps us consider all the epistemic uncertainties of our model. So I have a simple fault. Does this fault has a specified deep angle of 50 degrees? Sometimes I'm not sure about that. So I will use a logic tree in order to take into account all these cases. Do I have only a single seismic source? Even if I do have a single seismic source, and this could be a single fault. Does this fault has a specified deep angle, or is the hypocenter on exactly one point that I think with specified coordinates? All those uncertainties are concentrated on a logic tree and help me to take them into account. Any questions for that? Of course, we will make an example at the end and you will use it on your own. You can see how this is structured. It will be more easy. Okay. So now that I know my seismic sources, I know where they are. If I have a site that I want to predict the future shaking, and I know the sources in that site, I know the distances between my Rapture and the site that I want to study. Also, we know that each seismic source is associated with a distribution that gives me the magnitudes. So I have the magnitude and the distance. We are engineers, and when we want to design a structure, we don't use values like that as the magnitude and the distance. We want parameters that are associated with the ground motion. And that's exactly what a ground motion parameter does. We give them as inputs some characteristics of the earthquake, as its magnitude and the distance that it happens from our side, and it gives us a ground motion parameter. The natural Cornell's equation can give us back the natural logarithm of that ground motion parameter. In this case, this is PGA. So I have as inputs the magnitude and the distance, and the output is a ground motion parameter. But this is the mean value of that parameter. So I have an earthquake, let's say with magnitude 5. This graph is for magnitude 5 earthquakes. And at a distance 10 kilometers, I'm using Cornell's equation, and I find that the ln PGA has that value. Do you see my mouse?
Yes, you can see it.
Thank you.
Sorry, can I interject a little bit here, guys?
Yes.
Okay, sorry. Guys, remember our discussion back when we were discussing, let's say, the black box, and saying that this could be a physics-based simulation. Somebody could have an entire finite element model of your entire Rapture and run the Raptures in there, alternative scenarios, etc. And he or she would be able to figure out, let's say, the big ground acceleration at the specific site by doing the wave propagation. Okay, that is the expensive solution that needed a supercomputer. Now, this is what you see is the other solution, the alternative solution, which is what? It's the classic surrogate model approach. I like to call it, oh, by the way, you guys are familiar with Rio Mare? Hopefully. You must be familiar with Rio Mare, right? Tuna can. Okay. Now, the trick is the following. When you're really hungry and you really need something to, to eat, you have two options. One is to sit down, get your ingredients, get your chicken, marinate it, everything, put the food in there, put some rice, all these tricks. After an hour and a half, you eat. Or you can open a Rio Mare tuna can and you eat immediately. Now, what you see here is the Rio Mare tuna can of how to predict what a Rapture does at a site that is further away. Now, how good is that? Well, it depends. The one you see comes from Cornell et al. It's one of the oldest ones available, and it has very little information, very few information. If you go to the new ones, let's say coming from the TNGA project, those things are computer programs, actually. If we try to show you here, we need like 15 slides. It takes a report, I think it's like 100 pages plus, and it's a computer program. So you cannot even write down the expression, just to give you the tuna cans and tuna cans, okay? Back then, when this whole thing started, all you had was magnitude, distance. Now they have soil, They have deep angle, they have, are you in the hanging wall or the foot wall, the direction of Rapture, a bunch of things, okay? So they're getting better. But now what you're seeing here is pretty much the delineation of, remember the basic three components of PSHA when you do the integration was triple integral, actually triple integral plus a sigma. Sigma was for the fault, you sum up the faults. This is already discussed by Angeliki, that's fine. But the three basic parameters that you integrated over were the magnitude, the distance, and the epsilon. Now, what you see here is the median response given magnitude distance, and the extra that is coming up is what Akrivi is showing you on the right, Angeliki is showing on the right, is gonna be the epsilon, meaning the single solid line in the middle is the median that is provided by this equation on the left, right? And then plus minus, what you see here as plus minus are the standard deviations. And of course, actually there is a whole, if you know anything about regression, the regression doesn't just give you the mean, it also gives you an entire distribution, which means that given magnitude distance at any location, at the location of interest, you can actually estimate also how far upwards or downwards you can exceed or be below the average estimate. Remember, benign earthquakes, aggressive earthquakes, etc., etc. So this is the shaded parts, more or less, that Angeliki is showing you. Okay? So the further away you're from the bell curve, the more rare this earthquake is going to be, and vice versa. That's the whole idea, okay? So it's an interesting thing. It's a very interesting concept, but that's the way we do it. Again, remember, it's the Rio Mare, and it's called attenuation relationship or ground motion prediction equation. Ground motion prediction equation is probably the more recent term and probably better. Again, remember, the solid line is the mean. The dashed lines are the plus minus one standard deviation. The further away you go to the outskirts, more rare this motion is for the given MNR, right? For example, if you look at this one, oh, by the way, and a really important issue to remember, at some point, because the normal distribution that you see here can go to minus infinity plus infinity, there is some point where you truncate. Otherwise, you're starting saying stupid things like a magnitude 4 has a non-zero probability of producing 5G of PGA, which is kind of stupid if you know anything about earthquakes, okay? So all these things are gonna come into OpenQuake and this discussion. Again, remember, all this discussion has a lot to do about how you discretize and how you make a proper estimate out of the integral we showed earlier in the previous class. Sorry, Angeliki, go ahead.
Okay, so far we used logic trees only to take into consideration all the epistemic uncertainties of our seismic source model. We can use also logic trees to take into account all the possible ground motion prediction equations we use. Is it okay to use only one ground motion equation? We are not sure about that. We may want to use 2 or 3 or more. That's why we use a logic tree. I think there's an example. Okay, here we see an example. We have our seismic source. This is a logic tree. We will use that too. We have a seismic source and we take into account this is a fault. And we are not sure about the deep angle. That's why we will perform the analysis considering 3 possible deep angles. For each angle, we will use also 2 ground motion prediction equations. Each branch, those are called branches, is associated with a weight factor. So, whatever I use, it is associated with a weight factor I in order to produce my final output. Okay, I think this is the last one. Do you have any questions here?
Guys, let me come back a little bit and give you some little pointers here to understand what's going on. Now, there is it's all about correctly assembling the pieces, the discrete pieces going to the end. Now, there are two pieces that you need to assemble. One of them is the individual moments, magnitudes, etc., distances, epsilons, remember the faults, okay, sure. But there's also the part where you need to account for what's called epistemic uncertainty, which is we have alternative ideas about what the fault might be, or what the magnitude, the maximum magnitude will be produced by the fault, etc., etc. And of course, you could make this very elaborate, but usually what you do is you discretize that. So the best way to describe it is to say that there is the uncertainty that we explicitly model and we put into our GMPs, Gutenberg-Richter relationships, and there's also the uncertainty that we don't really model that much. And for that one, we're going to put it a little bit in the corner and call it logic tree, epistemic uncertainty. What it means is that we do not just build a single model of the point of the sources of the seismic source. We build multiple models, and we do our estimations not just for one of them, but for all of them, and then we sum them up together by appropriate weights. Of course, who assigns the weight? Okay, the experts. Okay, I have to say that. Why do we break it up into multiple models? Well, because would you ever believe a structural engineer or a seismologist who says that's the best model? I wouldn't. Nobody should. There are alternative models and there are alternative opinions. You have to account for them. So that's where the logic tree comes in. Each branch of a logic tree essentially tells you, okay, for example, here we end up with 1, 2, 3, 4, 5, 6 alternative models, and you got to run them all. That's what it says. You have to run them all, and you have to account for the variability. Now, remember always the trick. It's easy if you think about this about buildings. The uncertainty that you have within a single building, if you build a model of that, is actually fairly low. Why? Well, it's usually one engineer, built everything, etc., etc. But if you look within similar buildings, building to building, quite often the uncertainty is very large. It's the same here. Within a source model, quite often the uncertainty is fairly constrained, let's say. Why? Because the same seismologist made all the assumptions in that model. But if you move from model to model, which often means expert team to expert team, or actually even completely different sources, like this could be an area source, this could be a fault source, etc., you will start seeing a lot larger differences. So the whole point is to capture the within model uncertainty and between model uncertainty. Capture them all and have them in the results. So essentially, that's where the logic tree comes in. Now, if you want to go into the theory behind all that, you can have a lot of discussions. For example, theoretically, for this to work well, all the branches should be completely mutually exclusive, collectively exhaustive, etc., etc., which of course you cannot really do that because a lot of them are based on similar assumptions. And actually, there's a lot of discussion within researchers and the seismology community about, guys, are we really sure that model 1 to 6 are, really separate things, or do they overlap a lot? So, yeah, the current working approach is to say, okay, guys, there are just alternative views. Okay, just alternative views of different experts, and we just weigh them by how much we believe in each one. It can be a point of friction, by the way, but that's another discussion, not for me. Again, to give you an idea of how heated those discussions can get, I've seen those, I've heard those actually resolve into, let's say, day-long discussions of experts fighting with each other, fighting over every single data point, people complaining, oh my God, your assumption for that one are crap, you shouldn't do that. And the other guy shouted, no, your model is horrible. Anyway, somehow in the end, we assign the weights, we agree, and we say, okay, that's it. That's it. That's, let's say, you can think of it as a voting mechanism where each model gets a few votes. They all vote together. It's like the Electoral College in the US. They vote together and they figure out who's going to be the next president, or, if you will, the overall seismic source model. And this is, let's say, the fairest process that we can figure out to make all these things work together. Apologies for this long discussion, but it can be messy. Angeliki, go ahead.
Okay. I have a question, please. Sorry. So So for the open quake, like because there are like as you mentioned, like there are different intensity measures like PGA or something. So we predefine those intensity measures that we would like to model, or like open quake will take care of it.
Yes, we will do. We have to define them in our configuration file. We will see it in a few minutes. Well, actually, this is what
Okay, sorry.
Oh, don't worry. We have talked all about the previous stuff because they are our input for the analysis. We will use OpenQuake. This is our little black box. And we have to specify the source, the ground motion prediction equations, the logic tree, all of them, and a configuration file where we will specify the parameters of the analysis we want to run, and then we will take our results back. This is exactly what we will do now. We will see an example on how to run a seismic scenario, seismic hazard analysis. I'm sorry. We will perform a scenario seismic hazard analysis. Let me open another PDF file to see how we can do that. Give me a second. Okay. I think you can see that. Do you see my screen?
Yes.
Yes,
Okay.
yes, we
Let's
do.
see what we can do. Okay. To perform a scenario-based seismic hazard analysis. What is this? We have a single seismic source. We will have a simple fault that will produce earthquakes. And what we have from that analysis is we will take as an output, as a result, ground motion fields. We will have a single well-defined earthquake source, and we will know what is going on next to that at the area around that fault. So we have a single fault as an input, and we want to know what happens on the area around it. What are our inputs? Are the seismic source we have defined. It is a simple fault. Actually, this is a point source. And the ground motion prediction equation. And we will take back a number of ground motion fields. Why do we need a number and not just one? Well, we have used so far, we have many uncertainties that we take into account. Can we be sure that the output is only one? There is no uncertainty on the outputs. Of course there are. That's why we need many realizations for the output. Okay, now we can see how we can run an example on OpenQuake. The first thing we have is our seismic fault. We will specify its characteristics on a Rapture model.xml file. We will have a folder where we will have a Rapture model.xml file and some other files that we need in order to run our analysis with OpenQuake. Right here, we specify the characteristics of our Rapture. We have a simple fault. We will make some changes on it. You don't have to rewrite it. We will give it to you, and we will make there the changes. I'm sorry. We have a simple fault Rapture. This has a well-defined Rapture, and we know that it produces earthquakes with only magnitude 7. So, a simple fault with a well-defined Rapture that produces earthquakes of magnitude 7. I'm sorry. As we said, when we have a simple fault, we have to specify its orientation. The orientation here is 90 degrees. We know also that it's generated under a single point where our hypocenter is. The next thing we have to do is to specify the coordinates of that point. So orientation, coordinates for the hypocenter, and here we specify the inclination. Also, the other thing we have to do is to specify the coordinates of our fault trace. You see, this is the fault trace and this is the projection of our fault. Of the fault trace, this is our fault. So I need the magnitude. For a simple fault, I need the magnitude, the orientation, the coordinates of the hypocenter, the geometry of the fault trace, and the inclination. Actually, we have also two other parameters. This is the upper seismo depth and the lower. This is why we have a fault trace, but sometimes faults are not all over the surface of the Earth. We can't see them always. They might be on a lower depth. So we have a fault that doesn't start from the surface of the Earth. It starts 2 kilometers under that. So our fault is generated by a fault trace 2 kilometers under the surface of the Earth until 20 kilometers depth. This is the first file we need to have in order to run our analysis. We will use that. So do you have any questions so far?
Yes, I have, please, for the position. Is it the reference is the hypocenter or the middle of the fault? I mean, middle of the trace or whatever.
This is the hypocenter's coordinates. We consider that the rapture starts from that point, and it is a surface, is a plane surface where the center point is the hypocenter.
Yeah, that's what I mean. Okay, thanks.
You're welcome. Any other questions so far? Okay, I think we can move on. So we have a file that specifies the characteristic of our rapture, and we will have another file where we will specify all the parameters in order to run the calculation. This is called a job.ini file, and it's our basic input for OpenQuake in order to run the analysis. This is the format we have. And first of all, we have to give a small description. So here we say we have a scenario hazard configuration file. This is a heading that describes the type of the analysis we will perform and some of its characteristics. We can say whatever we want. We could say we have a seismic scenario-based hazard analysis for Athens. Or for Crete, we could say whatever we want. An important parameter is when we want to run a scenario-based analysis to specify the calculation mode. As you will see on the next lectures, we will run other types of analysis as classical hazard assessment or the aggregation, and we have to specify it always here. Now that we will perform a scenario-based analysis, we have to set the calculation mode into scenario. The next thing we have to do is to specify the site we want to study. So we have a site, we want to know its future shaking. We know that there is a simple fault, but where is this site? What do we want to study? In order to characterize it, we can say we probably want to study a whole region. If our site is a whole region, we consider that this is a polygon, and in order to specify it, to define it, we need the coordinates of the polygon's points. So we can have a square or a rectangular polygon, and we have to specify the point of its edges. So 4 points. It could be more if we have if we had another shape. We could have 5 or 10, as many points as we want. The other thing we have to do when we have a region that we want to study is to give a grid, which helps OpenQuake discretize it. As we saw before on the area surface, do you remember that grid? Of course, that was for the seismic sources, but this grid specifies the distance between the points of our grid. I have a square-shaped polygon that is my region. You will do that for your term project, and you have to give the spacing. Of course, sometimes you might don't want to calculate to see the outputs for a whole region. You probably want for only one side or for more sides. Let's say you want to perform a seismic hazard analysis for Athens and one for Thessaloniki. In this case, you can, well, those are really far, but anyway. In this case, you have to specify the coordinates of each side. If those sides are many, you can use a CSV file, a comma-separated file, and tell OpenQuake, well, you can find whatever I have said for you in this file, or you can use these options. So, in order to define the region or the site we want, we can do it here. Have you understood what we did so far?
Can I ask you something?
Yes.
The information of the grid
Yes.
is the seismic hazard acceleration or the shear wave velocity?
Can you repeat that?
Yes, I don't understand what is the information that we take from this program, and if we use the shear wave velocity, the VS.
Yes.
Is this the information that we'll take from the earthquake, from this black box?
Well, now we haven't specified those parameters yet. The first thing we have to do is to characterize the site we want to study. Let's say you want to study a region in Athens. To see the outputs, we will perform a seismic hazard assessment. The outputs will be, for example, spectral acceleration. If you want, it could be spectral acceleration at a given period, or PGA or PGV, whatever you want, but this is not specified yet. This is something we don't have to define in this case. The first thing we have to do is to specify the site we want the outputs, whatever those outputs are. Okay, so if you have a region or a site, the outputs will be defined later. If you see on another command way later, we will specify it. The first thing we have to do is to define the region or the site we want to study. If you
by the way, sorry to interject,
yes.
But the VS30 will come in later on, okay? It will come in as well, don't worry.
Okay, thank you.
You see that we want a ground motion field. In order to take a ground motion field, we have to specify where do we want this field to be generated, for what region this fault has to be generated. So we define this shape. This is a region, this is a square region, and we will define the coordinates of these 4 points. That's what we do here, right now. We specify the site we want to study. The next thing is to specify the rapture. We have a simple fault with a really well-defined rapture. In order to specify those characteristics, we have used this file. where we set all the characteristics of the fault and the rupture, and we tell OpenQuake, well, here is my file where I have set all the characteristics, and you can find the details in that file. When we specify a file with some parameters, this must be always on the folder of the analysis we will use. We will see it later, but please remember that. So I have specified the site or the region that I want. In the case of a region, I have specified also a grid spacing that helps OpenQuake run the analysis. And the next thing that I have to do is to give a mesh spacing also for the rupture. If you remember a few slides back, no, it was on the other slides, we have to give the mesh spacing for our fault also. This is used in order to help OpenQuake specify the distances between the points of our source. And actually now we will see the parameters. Do you see here is the VS30 value that we will use? But before I go there, we have a site that we want to study. In that site, we have a simple fault. And now we have to give the parameters of the site we want to study. What are those parameters? In this case, we will use the VS30 value. You know that the VS30 is the average shear velocity in the first 30 meters of the surface of the Earth. Would you like to repeat the question here? Is anything that you haven't understand yet? The things are pretty simple so far. We want to run a scenario-based seismic hazard assessment. And for that, we have to specify the region that we want to study and the seismic zones that there is in this site, in this region. So I have a region or a site, and I know that there is a rupture, a fault, a simple fault that produces earthquakes. For the region or the site I want to study, I have to specify some parameters in order to take my results back, even if this is a PGA or a peak ground velocity, whatever I want. So, in order to specify the VS30, I'm using a command that says it is measured. That means that for every point of the region that I want to study, the VS30 has the same value. And what is this value? It might be 760 or 400 or whatever my region, whatever is the appropriate value for the region I have to study. Do you understand that so far? Do you have any questions? We will see those commands again later, but it is nice if you understand what we are doing right now. Okay. If we didn't use the same value for all the sites of the region we want to study, we could use also a .xml file where we would have specified our inputs. So I have a region, and for every point I know that the VS30 values are different from site to site. In this case, I would use a .xml file where the inputs would be. I won't use those two options together. I will use only one of them. Okay. Let's move on. Well, another thing we have to do. Sometimes we can use those commands. Those are referred to a spatial correlation model. Well, a spatial correlation model tries to, well, it doesn't try. When I have a point that is correlated with its nearby objects, I'm saying that I have a spatial correlation model. Well, if here the PGA value has a specific well, let me restate it, because I think this is kind of confusing. I have a spatial correlation model. That means that every point is associated with its nearby points. They're not independent.
Sorry, can I come in here a bit, Angeliki? Guys, what you see here is actually it's a beautiful thing that needs to come in when you're not looking at specific points. So let's say you're looking at a lifeline, or you're looking at a city, an entire city. And the issue is that, let's say, a specific scenario happens. Okay. Now, if you use just let's say the GMP, I don't know, pick one, and you just sample randomly the epsilon values, this means that, okay, on average, the average structure will follow what magnitude and distance tell it to do. But locally, you will start seeing these weird hairy spikes because of this random selection every single, I don't know, let's say you have grid points that you, different sites, let's say, all over the city, all over your island, for example, every 100 meters. In reality, you should expect adjacent points to have nearby, for example, PGA values. But if you do not enforce that when you do the simulation, what you're going to get is, again, a very fuzzy output, which will differ extremely. For example, you see 1G here, 0.5G here, and then again 1G, and then 0.3, and then 0.2, and they will make zero sense. In reality, you would expect a more uniform, a more smooth way of this varying over the space. This is what's happening here. The ground motion correlation model, okay, is pretty much what does it for you. It helps you make sure that the spatial correlation is accounted for, so you won't see those really weird changes within, let's say, 100 meters or half a kilometer or 1 kilometer. You'll see smoothed out changes that still keep to the distribution, but also make sure that nearby things make sense. Okay? And actually, this comes from the Jairam Baker. Like, this is JB 2009. This is a Jairam Baker model. Baker, Jack Baker, Stanford University, nice guy. Jairam now works in Google, making the big money. Anyway, 2009, they produced this model, which pretty much tells you how correlated are those values the further away they're apart. Of course, the closer they are, the more correlated they go. The further away, the less correlated. So that's what you see there. And by enabling that, you're going to see that it makes a big difference. Okay, it makes your results look reasonable. Sorry, Angeliki, go ahead.
One question regarding this correlation. You mentioned that because when we calculate the, let's say, PG or something, it will depend on the, let's say, the location of the site and the magnitude. But like here we have a scenario source, which means that it's just one single event, right? So I'm wondering, like, how the correlation would, I mean, I don't fully understand, because I mean, in my understanding, I'm not sure, but in my understanding, like, the source that we consider is relatively small. So would that lead to like a huge randomness in the generated intensity?
Yeah. Let me help. It's easier. Let's say you kind of holding my cell phone. Let's say this is the fault. Okay, that's my cell phone, the fault. Let's say you have a site here, and you look at this, okay, as a plan. The site here and site over here, and let's say they're equidistant from the fault. Okay, from the I should not say fault, I should say rupture. The rupture is just part of the fault. So let's say they're equidistant from the rupture. Now, theoretically, they should have the exact same mean PGA, right? Because that's what the GMP will tell you. But the algorithm will tell you, okay, that's the mean. You should also sample epsilon. Remember epsilon, so it will add E times standard deviation. Now, here's what's going to happen. If you're looking at two sites that are on this side and they're nearby, you would expect them to be super correlated. I mean, you would expect them, let's say, if they're like 100 meters away, you would expect to see about the same PGA. So, sure, you should make sure that those epsilons that you select are about the same. So, nearby sites. Now, check out this one. Let's say you have one site here and one site on the other side. The distance now between them is fairly large, even though the distance from the fault is the same, right? Let's say they're both 10 kilometers, but among them, they're 20 kilometers, because one is on one side, one is on the other side. Now, those two, if they get exactly the same PGA or nearby, that'd be weird. Like, really? You wouldn't believe that. And you can see how this would be extremely weird, because it would lead to bands. You're looking at this being your Rapture, you would see two bands and bands here that are of the same color if you're looking at contours. That'd be really weird. So that's where this correlation model comes in. When you try to move away from the mean, because you have to, that's the randomness, otherwise everything would be perfectly estimated. That's when it makes sure that this randomness is applied in a coherent way, so nearby things get similar values at the end, far away things can get different, or if they happen to have the same, it's just a fluke, it's a random thing.
So this is for one single run, right? So the correlation...
For every single run, actually. For every single run. Every single run that you do, every single scenario, get this applied on top of it.
Okay. Now it's clear. Thank you so much.
Thank you.
Okay, now let's see the other parameters of our analysis. We said that we want to produce ground motion fields for the region we want to study. Well, those ground motion fields will be for different types of intensity measures. For example, I can have a ground motion field that shows the big ground acceleration, and the ground motion field that shows the spectral acceleration for 0.3 seconds period, and another one ground motion field for spectral acceleration at 0 seconds period. So when I want to produce a ground motion field, I have to specify the ground motion, the intensity measure type that it will be as an output. I have a region, I have a simple fault, and what I want to see is the big ground acceleration, for exactly. Let's go back. So if I have this ground motion field, this will show me the big ground acceleration at every side, at every single point, or the spectral acceleration, or whatever I want. The next thing we have to specify is the truncation level. Well, before I go there, I have to set the maximum distance of the fault. This is used to reject all the possible far-field earthquakes that may happen. The largest distance between the Rapture and the target calculation site. So when I have a Rapture, this produces earthquakes, and the most far away point that I want to study is 200 kilometers away from it. I have to use, in order to produce the intensity measure types, a ground motion prediction equation. And in this case, we will use Burr-Atkinson 2008 ground motion equation. Of course, we have to set the number of ground motion fields that we will use. Those can be as many as we want. One is not a good option. 2, 3, 10, 1,000, as much as we want. Let's go back to the truncation level. The truncation level is, as we discussed earlier, the number of standard deviations around the mean value. As Mr. Van Vagicles explained to you, we have this line that connects the mean values of the intensity measure type we want to study, and around it we use mean values plus minus a number of standard deviations. In this case, where we have set truncation level equal to 3, that means that we want the area that expands from mean value minus 3 standard deviations until the area of mean plus 3 standard deviations. So I have bounds from minus 3 standard deviations until 3 standard deviations. In this case, I will use all the values that are the 99.7% of the values that I have been produced. This is from your statistics class.
Guys, sorry, Angeliki,
Yes.
I'll be taking off in a bit. It's about time, whenever you're finished with this slide, I'd say you take a break. Okay.
I think this is the final, so we can have a break, and after this break, we will run our OpenQuake files and produce our own ground motion fields.
Okay. Excellent. Guys, just to let you know that this discussion of the truncation is really, really important, because if you go to real seismologists and talk to them, we are surrogate seismologists here, okay, more structural engineers. If you talk to real seismologists, they'll come back and tell you how much is that plus bound, the plus 3 standard deviations, pretty much tells you, quite often tells you the upper bound of what can happen in your site, okay? It pretty much shuts down what can happen at the top. So it's really important, because it tells you, on average, we've observed this much, plus 3 standard deviations. That's a lot. That can be a lot. So there's been a lot of calls and discussions of how you figure that out. Should you maybe, use a different distribution? But then again, this is discussion that, how PSHA is going to be running in the future. For now, it's a log-normal distribution with a cutoff plus minus 3. Okay, that's all. Okay, guys, ciao, Angeliki. Please hold the fort. Any questions? We also take emails. Akrivi will also be around to help. Ciao from me.
Goodbye, Mr. Rambatskis. So we can have a small break, and after that we can run our examples, our demos for OpenQuake. So you're free for a few minutes. Okay, I think it's time to continue after the short break. Let me share my screen. Okay. Right now, we will run a demo in order to obtain 10 ground motion fields for PGA and spectral acceleration at 1 second period. How can we do that? I'm sure all of you have installed OpenQuake and Qgis in your computers. I believe yes. So the first thing we have to do is to download from the documents on my courses the file we will run. The file we need for this example is called scenario.sha.zip. This is what you have to download in order to run the analysis. So please download it. And we will continue. Whenever you're ready, please tell me. Now that we have downloaded our file, the first thing we have to do is to unzip it in order to see what there is in the file. Okay. In here, we see 3 other files. The first one gives a small description of what we will do. We will run a demo exercise for a scenario-based seismic hazard analysis in order to simulate a single rupture from a simple fault source. In this example, we will compute 10 ground motion fields for for those intensity measure types. And the analysis will not last more than 1 minute. Here, also we can see the files we talked about earlier. The first is the Rapture model. No. Wait, let me open it with Notepad++. I usually use Notepad++ because it is easier to see and make changes on the files. If you don't have it, you can use whatever you want, but this is free, so if you want, you can download it too, if it helps you. As we discussed earlier, we have a simple fault with a magnitude of 7, a given orientation of 90 degrees, and an inclination of 90 degrees. Those are the coordinates of the hypocenter, and those are the coordinates for the fault trace. Also, we have an upper and lower seismo depth. We have seen that, we know how it looks like, and we don't have to make any changes now. Let's see something else. This is the configuration file we have always to use. Well, when we want to run an analysis with OpenQuake, we have to give a folder to the program in order to run. That's why in this folder, we have to set those files. If we don't have them, the analysis won't run. Let's see the job.ini file. First of all, we have give a small description. We will perform a scenario calculation with a simple fault rapture. The calculation mode is set to scenario, and this is used in order to OpenQuake to use a random generator. This is something that you don't care about, just leave it as it is. The next thing we have to do is to specify our region. We said we will use a square-shaped polygon with 4 edges, and those are the coordinates of the edges. First, we have to give the longitude and then the latitude. We also give a grid spacing. This defines the distance between the points of the grids. And then we have to set the parameters for the Rapture. We have give the file that we have specified those parameters, and the Rapture mesh spacing for the Rapture, obviously. You should be careful. The lower the value of the spacing for the area we want to study and for the Rapture, the higher the computational time, but also the higher the result, the more precise the result we will get be. Next, we have to specify the parameters of the site we will study. We have seen before those commands. And the next thing we have to do is to specify the intensity measure types that our ground motion fields will show. We want ground motion field, we want 10 ground motion fields that will show PGA, and 10 ground motion fields that will show spectral acceleration at 0.1 seconds. We have set truncation level equal to 3, but the first time we will run the analysis, I want you to change the value of truncation level. Wait, I forgot to tell you. I would prefer if you run the analysis as I ran it, if you have any problems or anything else. I don't know, is anyone that follows my steps? First of all,
we do.
Okay.
Can I ask something?
Of course.
Do we use meters in order to define the region, or kilometers? Maybe kilometers.
Well, it's actually kilometers for the region and the Rapture. We use meters per second for the VS30 value. And also maximum distance, I think, is kilometers.
Okay, thank you.
You're welcome. So the first thing we have to do is to change the truncation level to 0. Next, we have set the maximum distance and the ground motion prediction equation we will use. Well, OpenQuake is written in Python, so when we want to make a comment, we just have to use the hashtag sign. So if you see here that we have hashtag signs, that means that OpenQuake won't consider those commands in the analysis. I'm telling you because we will run the first time the analysis without those commands, and the next time we will perform it with those commands enabled. So now you have made this little change in the truncation level from 3 to 0. We save the file, and in order to run the analysis, we have to zip again the file using the correct files, to zip the folder with the correct files in it. In order to do that and not to have any problems with zip or RAR, I suggest you to right-click on the file, use the send to or apostoli pros for those who speak Greek, and zip file. Okay, now we have a zipped file. In order not to confuse our files, I will change the name and I will add that we have no correlation because we have made as comments those commands. We have a scenario SHA analysis with no correlation and truncation level of 0. This is something I do in order not to have any problems with the analysis I will run. So we have a zip file, and now it's time to run the analysis. How can we do that? Now that you have downloaded OpenQuake, you must have those two options. Actually, they're also here. The wave view and the console. The way we will run our analysis is through the wave view. Do you all have those programs on your computer?
Yes.
Okay. So click on the wave view and those black window will open. Wait a few minutes. Internet browser will open. Okay. When all of you have done this, please, in order to move on. Are all of you
ρωτήσω
okay with
κάτι.
that? Ναι.
Εμένα δεν μου έχει βγάλει αυτά τα εικονίδια στην επιφάνεια εργασίας όταν το έκανα εγκατάσταση. Πρέπει κάπως να τα βρω να τα κάνω συντόμευση, έτσι.
Yes, the question is that those icons are not on the desktop. You can search on your computer and you can do that.
Okay, thank you.
Probably if you scroll down and go to OpenQuake, you will see them. If not, then we can see together if there any other problem. Are we all okay with that? Has this window on your browsers open? Yes, no.
Yes.
It came as an empty page on mine, actually. List of calculations from desktop, it's an empty page.
Oh, yes. This is something else. Because I have run many calculations, I have run some other calculations on the past. That's why I have those here. For you that it's the first time that you run OpenQuake, this must be empty. Don't worry about it. Also, one thing you have to see here is that some of my analysis, excuse me for a minute to drink some water. Better now. Okay, you see those analyses are green, are with green color. That means that the analysis has been completed. When you see a red color, that means that something was wrong. So let's run our first calculation. In order to do that, click on Run a Calculation. And then you have to find where you have stored the file we just made. Click on it, and the analysis will run. So if you status, it says created. And now we will wait until our analysis is done. Is there any problem so far? If you see here, my analysis is done. It is already completed, but I want to know if yours is too in order to see together the outputs. Do you have any problems until now running the analysis? I see something on the chat. Okay, someone was telling that.
Can I ask something?
Of course.
Do we have to have opened the window of how was the program? Open
Those black.
The black window.
Yes, yes. This must
be opened. Ah,
yes.
that's why. Okay.
Okay. You can rerun the calculation. Yes, this is a problem. You have to let it open. Let it be open. Okay. Someone said that the analysis hasn't been completed yet. Okay, let me see something. I don't remember how many ground motions we asked. Okay, we have 10 ground motion fields. That's why. Is anyone that the analysis is done? Has been completed? One. If you have a problem running it, please tell me in order to see what happens. Okay, nothing. No one? Am I talking on my own? Okay, it's completed. Thank you very much. So, when you will run an analysis, probably it won't last so much. It will take a lot more time, and specifically in your term project, you will have to wait a lot of time. If something goes wrong, you can press the console and see what OpenQuakes tell you. Well, actually, this is kind of hard, but if something happens, you can see what was wrong. Now that everything is okay, we don't have to see anything. Let's download the outputs. You see here that the outputs are those. First of all, we have the input files we gave to the program in order to run the analysis. If we want another time to see what we have done, we can download it from here. The next thing is a full report that says what has been on the calculations. It's something that we won't use. The thing we need to have and to download are the ground motion fields. That's why we have to download them. Okay. I'm sorry, I see a comment. I see something on the chat. Let me find the chat now. Because it is difficult for me to follow the chat, it would be nicer if you could open your microphones and tell me. Right now, it's kind of difficult. Okay.
I am running not on Windows, but
Okay.
now I already have the HD5, but I couldn't find those one that you have. Yeah, so that's my problem.
You have the outputs from the analysis, you run it and Those are not the outputs?
I mean, it said like the HD file is stored here. But so it's there, those files that you are showing? Is it
Would you
in
like
the
to share
HDF file?
screen? Would you like to share screen your computer to see what is the problem? Because I couldn't understand what is going on. Would you like to show us your screen?
Yes, please.
Thank you. Yes, of course. Okay. You run the analysis from the command window?
Yes, because
Okay.
I don't have Windows. And
Okay, so
it's here, right?
yes, the analysis is done, is completed. You can see down here that those are the files
But
that we have produced. The outputs are probably on the file you have run the analysis. So if you click on the file we just zipped, you haven't zipped the file in order to run the analysis. The outputs must be in it.
Oh, okay. Okay, I will check. Thank you.
Okay, you're welcome. Let me continue share screen my. Okay. Are there any questions so far? Is there anyone that has any problem? Well, we have downloaded our ground motion fields. I believe everyone has them. And let's see what we have now. The first thing we have to do is to unzip them. Okay. In here, we see we have 3 other files. The first one, is there anyone that has any question? I'm hearing something? No, this is my imagination. Okay. First of all, we have the site mesh file. In here, we have the points of the grid. We have set a region that we want to study, and we have used a grid for those regions. So many points with its coordinates are here. In order to see the results better, we can make some changes. If you want to, this is a comma separated file and we have to change it a little bit. So click on data. If you want to change it, click on data, text to columns. This is delimited. Use next. Because this is a CSV file, a comma separated file, we have to use the option comma, next, and this is a problem. If you are using a comma on your Excel as a delimiter, you have to click on the advanced option and change the comma with a dot. Something that I'm doing because my Excel uses comma and not a dot. So I'm changing it. I'm showing it for the second time. If you don't have that problem, you don't have to do that. And I'm pressing finish. Now you see that I have all the results in a format that my Excel understands. Is it okay so far? Do you understand it? Do you have any problem? This is not something difficult. So in this file, that it is called site mesh, on your outputs, this value won't be 31. This must be probably 1. This is the first analysis you ran. So here we have the outputs for the site mesh. The next thing that it is important for us now are the ground motion fields, ground motion values. So if you open this file now and make exactly the same change we did before, what is it? What is this? I'm clicking on the first column, use the option text to columns on the data, click on next, use comma as a delimiter, next, use the advanced option because my Excel is stupid. Change dot with a comma, press OK and finish. Okay? Well, what do we see here? First of all, on the event ID, we see the number 0. If you scroll down, you will see that it is until 9. We have events from 0 to 9. 0, 1, 2, 3, etc. This is the ground motion fields we want. We ask 10 ground motion fields from OpenQuake, and this is what we have. Because it is written in Python, the first number, it's not the unit, it's 0. So I don't have 1, 2, 3, 4 until 10. I have 0, 1, 2, 3 until 9. I have 10 ground motion fields. For each ground motion field, I have the site IDs of the region. Those are the points of the grid of the region I want to study. And next to it, I have the parameters, the intensity measure types I asked from OpenQuake to give me the outputs for. You understand that it's not easy for us to see what are the outputs. That's why we will visualize them in QGIS, and that's why we have told you to download it. So far, we saw 2 output files, the site mesh and the ground motion field. The ground motion fields. Do you have any questions so far? I know it's not difficult, but it's something you see for the first time.
Can you show us again how to separate in different columns the data?
Of course, let me close it and open it again. I'm clicking on the ground motion fields at every point. This is a comma-separated file. So I click on the first column. I'm going here on data. Click on text to columns. Have you done it so far?
Yes.
Okay.
Yes.
I'm clicking next. On the delimiters, I use the option comma and next. I don't know if your Excel uses comma or a dot.
Okay, thank you. Yeah, okay, that's fine.
Okay, perfect. I have to change it again. Clicking OK and finish. And this is how I do it. Okay? Any questions so far? Something that you don't understand? Or anything else? Okay. I'm clicking. I won't save it. But now what I want you to do is to open QGIS. If you have downloaded QGIS, you will see that there are many options. The main option we will use is the desktop option without any other comments. So click on it and we have to wait a few minutes until it is opened. Seriously, if you have any question, please ask me. If you don't understand something, okay, it takes some time to open. And we will start a new project. Have you done it?
Yes.
Okay. Okay, so we can continue. The first time you will run QGIS, you have to enable, first of all, I think you already have installed the plugins for OpenQuake. If you haven't, click on plugins. On the search button, search OpenQuake. I have already installed it, but if you don't, please install the plugin. I'm sure all of you have done it. I don't believe that there is any problem. And the first time you will run also QGIS, please right-click on it, and this window will open. I want you to click on the manage. Let me think. You have to click on γραμμή εργαλείων διαχείρισης επιπέδων, or in English I believe is manage layers toolbar. I have already clicked on it, so I will do it again in order you to see that. Click on it, and those tools are here in order to use them. I'm sorry. Okay, this was easy. Does anyone has a problem?
Can you show it again?
Of course. Right click on it, right click on QGIS. Probably if you do it here, it won't be shown. Do it here. Click on γραμμή εργαλείων διαχείρισης επιπέδων or manage layer toolbar. This is the option. I unclicked it and I will do it again. Okay. Are you okay?
Okay, thank you.
You're welcome. What we have to do now is to add a layer. Whenever we want to do that, we have to use this option, because I don't know how it is called in English right now. Remember that we will use this icon that looks like a comma. So click on it and this window opens. Okay? Here on the dots, we will search the layer we want to see. Okay. Let's find the files we have downloaded so far. Let me find the file I want. Where is the file I want? Okay. Do you remember the outputs file? In here, the first thing I want to do is to see the site mesh of the region I want. Click on site mesh. Let's do it again. Use this icon. It looks like a comma. Click on it. Click on search here and find the file we have installed from OpenQuake. Click on site mesh. And we have to make some changes over here. The first thing you have to do is to use the file format as a CSV file. That way, down here, you can see that you have all your columns separated. Okay. Next, you have to click on those two options. The names of the columns will be site ID, longitude, and latitude. And we want OpenQuake to detect the field types. The next thing we have to do is to define the geometry. You see that in here we have a site ID and the coordinates, longitude and latitude. That's why on the geometry definitions, we have to use the first option. If you click on it, you have to specify that X is longitude and Y is latitude. Have you all done that so far? It is easy. We want a layer that shows us the grid of the region we want to study. We have to use a comma separate to find the file. We need site mesh. It is a comma separated file. We have to click on those options. It is something that QGIS needs in order to understand the type that we have set. We have to set the geometry definition on coordinates and specifying the longitude and latitude. If you have done it, we will click on add and see this is the site mesh of the region we want. It is a square region. Okay. And now we want also to see the ground motion fields. In order to do that, we have to also click on the comma icon. And now we will give as an input the ground motion field data file. Click on it. And now we have to make some other changes. This is also a comma separated file. Don't worry about those commands, but in this case, if you see, we have the events ID, the site ID, and intensity measure types. There is nowhere geometry coordinates. That's why we have to use the no geometry option. Okay? Have you all done that? Is there any problem so far?
I have a problem with the previous step.
Okay.
I cannot get, δεν μου βγάζει την προσθήκη, μάλλον κάτι δεν πάει σωστά.
Okay, let me, if I want to remove that, right click on it and remove layer. We will do it again. So, click on the comma icon. Have you done it so far?
Can you start with the even before that, if you don't mind? Like how to get those, the comma thing.
The comma thing on Excel?
No.
Okay.
Like the step before.
Though you mean to have those icons?
Yes.
Okay.
Sorry.
Don't worry. You can also do that from those options, but it is easier if you have them all here. So right click on it. Right click on QGIS. And is this showing on your computer?
No.
Okay.
Just copy coordinates. That's what I have.
Okay, you're doing it here.
Yes.
Please try over here somewhere.
Okay.
Possibly here that says layers or epipeda. So if you click here, somewhere here, I believe it will be shown.
Yeah. Sorry. Yes,
Okay.
yes.
Don't worry. So please enable this command, manage layers toolbar. It is 2, 3, 4, 5, 6, 7, 8. I think it is the 8th option. So can you see it now?
No.
No, not again?
I mean, I don't see. Manage layer toolbar. Yes.
Okay.
Yes, I have the comma now.
Perfect. Okay, so let's do it again. You have to click on the comma icon. It is not a comma icon. I'm just telling it like that. Click on the icon, and now you have to click on the dots over here. This is a search button. Find the file that you have downloaded from, or you have from your analysis if you're using the command line, the command tool, and find the site mesh. Click add, and the first thing for the site mesh is to click on comma, it is a comma separated file. You have to enable those two options on the record and field options. You have on the geometry definition to click on coordinates. It is longitude and latitude, and you will see something like that in here. If you click add, this must be shown. Do you all see that?
I can see that, yeah.
Okay, that's perfect. The next thing we have done, or you can do now, is to click again on the comma icon and find the GMF data. Click on it. It is also a comma separated file. We don't mess with those commands. And the other thing we have to do is to click on no geometry. Because we don't have any geometry here, we will connect those IDs with this layer. Click on add, and you see that nothing happens. Weird. No, actually, it's not weird, because as I told you, we have to connect those layers. On the site mesh file, we have the IDs of each point. This is point 0, point 1, etc. And their coordinates. Here we have only for each ground motion field the intensity measure type and the site ID. That's why we have to click on site mesh. Click on it. And now right click with your mouse and click on properties. Right click on site mesh and properties. Do that. And if you see over here, click on joins or synthesis in Greek. If you click on joins, right here down on your screen, see a cross. If you click on it, you see that we want to merge this layer, the ground motion field data, with the site ID. You have to click site ID twice. So we will connect this layer with this layer, with the site mesh layer, and to use the site ID column. So in order to do that again, right click on site mesh, click on joins, click over here, add new join, use the site ID options, and click OK, and apply. Also nothing happens. Before we connect them, I want you to do something else. The first thing, you remember that we have asked OpenQuake for 10 ground motion fields. I want from those fields only the first one. In order to do that, right-click on ground motion field data, and there is an option that says filter. If you click on filter, this window opens. Click on event ID. That way I can extract from the outputs only the first event ID, only the first ground motion field. So right click on ground motion fields data, click the filter option, click here event ID, use equal, and you can use whatever ground motion field you want. I will use the first ground motion field. We said that the number is not 1, it's 0, but I could use 3, 4, 6, or whatever I want. Right now, yes?
Can I interrupt? On the fields, instead of just event ID, it shows me event ID, ερωτηματικό, site ID, ερωτηματικό, κλπ.
Okay, I'm stopping sharing, and please share your screen in order to see what is going on.
I'm using another computer, so...
Okay.
Just now.
It is probably something on the commands we used on QGIS. So if you are not able to share your screen, I will continue, but if you can do it, please tell us. So right now we have filtered, actually I didn't, I stopped it. I want the first event ID. I'm clicking on 0 and OK. If you filter it, you will see this icon over here in order to be sure about it. What we have to do now is to return on the site mesh, return on it, click on properties, and we won't go on joins. If you have joined those two layers, this must be over here. If it isn't, you have to join those layers. Now we have to click on symbols. If you click here, you have to use this option. This option is called με βαθμίδες, or in English it is graduated. Με βαθμίδες or graduated. And now I have to use what what is the parameter of the ground motion fields that I want to see. If you click on here, you will see that there are many options. What I want to do is to see the peak ground acceleration. I have used peak ground acceleration, and over here on the colors ramp, I'm using the spectral one. So I clicked on it, spectral, and now I want to invert the color ramp. The lower values will have a blue color and the higher will have a red one. Okay, we use that. Click here on ίδιο μεσοδιάστημα. Okay, probably this is equivalent on your computers if it is in English. Click on classify. Those results will be here. You have some classes. You can use as many as you want. This is the number of the classes you will have. Let's use a number of 10 classes. And click on apply. If you do that, you see that we have our first ground motion field. Okay. Probably you won't have a problem. But if you do, please guys tell me, because I really have to go. I have another seminar 5 minutes earlier. Do you have any questions? Have you already do that?
Yes.
Okay, so you're okay so far. If you have any questions, I have sent you my email on the chat. You can ask me anything. I'm so sorry, I really have to go. But the next time we will see more stuff about QGIS and OpenQuake. We will see all the other results we have done. We will see the maps, the ground motion fields for spectral accelerations. We can see other ground motion fields except the first one we use. We will do many things. Are you okay so far?
But basically, can you show us from where we define, after we put the GMF data file,
Okay.
can you show us again the steps?
Okay. You have to click on the GMF data, filter the first event, right-click on GMF data, click on filter. Okay, we'll do it really fast. Event ID, I'm sorry. Click on event ID, use equal and press 0.
Okay.
Now, it's not filter on mine. Okay, event ID equal to 0. Click OK, now it is filtered, I can see it.
Mm-hmm.
The next thing you have to do is right-click on sitemaps.
Yes.
Click on properties. Have you joined the layers? If you haven't, click on joins.
Yes.
Click over here on the add new join.
Yes.
If you have done it, if you haven't.
ID on both of them, am I correct?
Okay. Next, click on symbols.
Symbols, yes.
Yes. Click on graduated or με βαθμίδες in Greek. The next, you have to click on the intensity measure type you want. I used PGA. If you don't see it,
I see 4 options. Site ID, longitude, latitude, GMF data, 1 event ID.
Okay. Well, I don't know exactly what is happening now, but if you follow the steps again, and you can do it please send me an email in order to find what is happening.
Okay.
I'm so sorry, I really have to go.
Okay.
So sorry, guys. We will talk together again next time, I believe. I hope no one has a problem. If you do have, I have sent you my email on the chat. So I will stop sharing now. Thank you very much. We will talk again next time.
Thank you. Bye.
Thank you.
Thank you.
Thank you.
Goodbye.
Thank you. Have a nice day.
You too.
Bye.
Bye.
Thank you.